We've talked about temperature scales, and we've seen how temperature is just a measure of thermal energy of a substance, which means that the hotter the object is, the greater the random motion of the atoms or molecules in that object. Heat, on the other hand, is the transfer or exchange of thermal energy caused by temperature difference. So it's given in units of energy, like the joule. And more specifically, we have heat capacity, the quantity of heat that is required to change the temperature of a given amount of substance by 1 degree Celsius. And we can make this material specific by making it a specific heat capacity, or for short we can say it's specific heat, which is the quantity of heat required to change the temperature of 1 gram of substance by 1 degree Celsius. And in other words, in layman's terms, all what specific heat is saying is how much heat can a substance stand before it changes its temperature. So why do we have pots that have plastic handles on them? Well, your metal, which is what your pot is made of, has lower heat capacity. It cannot stand that much heat before changing its temperature, getting too hot for you to touch. So they put plastic handles on it. The plastic handles have higher specific heat capacity, which means they can stand a little bit more heat from your stove before they actually have to change temperature. And we use this equation, Q equals MCAT, to measure how much heat a substance gives off from a certain temperature change. So let's see what all these variables means. Q is your heat, which is usually given in joules. Your mass, or M, is your mass of that substance in grams. Your C here, that's your specific heat capacity, or specific heat. That's given in joules per gram per degree Celsius. And this is found in table 3.4 in your book. And it's, again, specific for different materials that you use. The delta T here, this is how it's read. Delta T, if you've never seen, this is a Greek symbol, and it means change. Change in temperature. And the changes in temperature is your final temperature minus your initial temperature. So this is your final temp minus your initial temperature. So what is this saying is, before I turned on my stove, my pot was at 70 degrees Fahrenheit or so, or 22 degrees Celsius, room temperature. And then I turned on my stove, and then my pot heated up to, let's say, 70 degrees Celsius. So that is my final temperature, and my initial temperature is what I started with. Now let us see a couple of examples where we use this equation. Okay, so you are making a cup of tea and you want to know how much heat energy will warm 235 grams of water from 25 degrees Celsius to 100 degrees Celsius. Okay, so let's always write our givens, always, always, always. So we have our mass here of 235 grams. We have our initial temperature, because it says from 25 degrees Celsius to 100 degrees Celsius. So our T final is going to be 100 degrees Celsius. Now, we are wanting to find out what our heat, because it's saying you want to know how much heat. Remember, Q equals heat. So how much heat, and we're going to say in joules, will you need to heat up that much water from 25 degrees Celsius to 100 degrees Celsius. Okay, now we are missing one thing that you can look up from the table always. Now, we were given the substance, water. So we go to our table 3.4 in the book, and we found that the heat capacity for water is 4.184 joules per gram per degree Celsius. Okay, now we have our equation, which is just T final minus T initial, and we are trying to solve for Q. So let us make sure we have our mass, we have our heat capacity, we have our final temperature, and our initial temperature, and all we have to solve for is Q. So perfect, we have one unknown only. So let's plug everything in. 235 grams times our C, which is 4.184 joules per gram per degree Celsius, and we have our T final is 100 minus our T initial. This is in degrees Celsius. Here's what you always want to do. You always want to make sure that your units cancel out, and usually your C will give you the units that you need to convert everything else to. So notice our grams cancel, our degrees Celsius cancels, and we're left with joules, which is what our desired unit is, what we want our final unit to be. So we end up with 7.4 times 10 to the 4th joules for the final answer. Don't forget to put your units, and don't forget to put your correct number of significant figures. Okay, let us do another example. A chemistry student finds a rock that she suspects to be gold. She finds the mass of the rock to be 4.3 grams. Then she finds the temperature of the rock rises from 25 degrees Celsius to 52 degrees Celsius upon absorption of 174 joules of heat. Find the heat capacity of the rock. Is the rock gold? Okay, so let's write our givens as always. So the first thing is the mass, which is 14.3 grams. Then we find that the initial temperature is 25 degrees Celsius. The final temperature is 52 degrees Celsius. And we find that upon absorption of 174 joules of heat, so our Q is 174 joules. And we want to know what is the heat capacity of the rock, the specific heat of the rock. We don't know what the material is, so we're going to use all these factors to determine what material this is. So this is our equation. And let us see what we have here. Okay, so we have the mass, we have the T final, T initial, and Q. We're trying to solve for C, which is the specific heat. So let us rearrange our equation to solve for C. And very simply, we just divide this value on both sides. And we end up with C is equal to Q over M times T final minus T initial. Now we're ready to plug in our values. We have 174 joules over our mass of 14.3 grams times our T final, which is 52, minus T initial of 25. We plug this in and we end up with 0.4507 joules per gram per degree Celsius. But we have to round this to two significant figures. So it becomes this number. And then we go and we look up in table 4.3 what is the specific heat for, or table 3.4, what is the specific heat for gold, and we see if it matches or not. And in our book it says that gold has a specific heat of 0.128 grams per degree, or joules per gram per degree Celsius. Let me rewrite that. 0.128 joules per gram per degree Celsius. Now you find these numbers do not match, so this is not gold. Okay, go ahead and try this on your own. And let's see, we have a 328 gram sample of water absorbs 5.78 times 10 to the third joules of heat. Calculate the change in temperature for water. And the second part of the problem, if the water is initially at 25 degrees Celsius, what is the final temperature? So it's a two-part problem. A and this is B here. So let's write our givens. We have a mass of 328 grams. We have, this is water, so we know our heat capacity is 4.184 joules per gram per degree Celsius. We found that in table 3.4. We know our Q is 5.78 times 10 to the third joules. Now we need to find out what our temperature changes. Okay, so we have Q equals MCAT, and in order to solve for temperature change, we have Q, we have M, and we have C. We just need to solve for the change in temperature, and that is, we have to divide both sides by MC. So our delta T becomes Q over MC. Okay, now we plug in our values. We have 5.78 times 10 to the third joules over 328 grams times C, which is 4.184 joules per gram per degree Celsius. Notice our grams cancel and our joules cancel, and we're left with degrees Celsius. So we end up having a temperature change of 4.21 degrees Celsius. Okay, now for B, we have all the same components, but now we want to solve for what if we had an initial temperature of 25 degrees Celsius? What is our final temperature? Well, we already found that delta T, what delta T is from here, because it's all the same under the same conditions. We still have the same C, the same Q, and the same M. So our delta T is T final minus T initial. And so we simply solve for our T final by adding T initial to both sides. So we end up with plus T initial. And we plug in 4.21 plus our T initial of 25.0 degrees Celsius. So our T final becomes 29.2 degrees Celsius. And that's how we go about this problem. Remember, you cannot make this assumption unless all your conditions are the same.